Okay, week 3, video number 2. Looks frighteningly similar at the start. Wearing all the same clothes, same terrible hair, same graph even, but the function is a little different. You've got a graph of this function h of x, which is based on the accumulation of area from 1 to whatever x we pick of f of t dt, and this is the same f graph. So the big whopping difference here is that that's a 1 on the bottom instead of a -6. -6 I feel is like kind of easier because you're anchored to what is theoretically the start of the graph, but here you're being anchored to 1. So it's kind of a little weird. But we're basically asked the exact same question. We want to find h of -6. We want to find h of -4. We want to find h of -2. We want to find h of 1. It's just all the same questions, just with this h function. So let's talk about how when we change the sort of anchor point, the lower limit of integration is what it's technically called. If we change that anchor point, how it affects the function. So let's do h of -6. h of -6 is telling you to integrate this function from 1 to -6, f of t dt. So this is kind of funny when we're starting at -6. This is kind of easy. This was the easiest question on the front / first page, and it's the weirdest question, or it's kind of weird here. Now, if you want, you have the option to flip the limits and just go from -6 to 1, f of t dt, and that would be okay, or we can kind of just like think about it in an alternate way. So either way, we should get the same answer. So I guess I'll kind of do it both ways. So when we're going from 1 to -6, we're essentially going backwards. So you're talking about all of this space. That's it. So if we're looking at it this way, we're now talking about this and this, but we're sort of flowing this way. So this guy's height is -2, but its base is also this guy's height is -3. But its base is also negative because we're going backwards. So this base is -3. Here, for this big giant triangle here, its base is negative. It's 1, 2, 3, 4 wide, but you're going right to left, which effectively makes you negative. And then the height is the normal positive thing. The height of this triangle is 4. So this should be 1/2 of 4 times -4 plus 1/2 of -3 times -3. So that's going to wind up being half of -16, which is -8, and half of 9. So that's just 4.5. So -8 plus 4.5 winds up being -3.5. So we'll make a little bank over here of all our answers. So h of -6 is -3.5. Then we want to kind of do this for those other sort of regions. So now we want to integrate h, we want to integrate f, I guess, but we want to find h of -4, which means you want to integrate from 1 to -4 of this f function. So what you're basically doing is you're still anchored to 1, and now we're not really like accumulating area, we're losing area. So we wind up losing all this space. So it's kind of weird. That's the major difference from starting not at the left endpoint of the graph and starting somewhere in the middle, is you almost already have this like pre-established area, and you wind up losing it as you move from left to right. And losing it's going to just change our answer. So we basically just have this first guy, which is 2 by 4, except this is left to right. We're talking about going this way. So this base, remember the bases of these little rectangles is always that number minus that number divided by how many rectangles you want. That's going to be negative whenever top number is less than bottom number. Again, you have the option of just flipping the limits, putting a negative in front. That's fine too. And then we also have this extra rectangle, which is the same, triangle, which is the same triangle we had before. This base is negative because we're backwards, and this height is also negative because we're down. So this is going to wind up being half of 4 by negative 2 plus half of negative 3 by negative 3. So this should be negative 8 times a half. So that's just negative 4 plus 4.5, just like it was before. That should be a half. So h of negative 4 is just 0.5. And then we're going to just play this game for those other values. If it's easier for you to think about it by flipping the limits, that's how kind of a lot of people like to treat it. But I just want to sort of focus on the right to left aspect of this for the purposes of this video. So next we want to do h of negative 2, I believe. So h of negative 2 is just you integrating from 1 to negative 2 of f of t dt. So basically, again, we wind up losing what area we already have established. We wind up not talking about this region anymore. So it's like we're losing these rectangles. So now we're just talking about what's this area, which is 3 by 3. We're going backwards because this number is less than this number, which makes this negative. And we're still upside down, so that's negative. So this should be half of negative 3 by negative 3, which is, you're probably sick of seeing that, 4.5, but h of negative 2 is 4.5. Then we wind up doing h of 1, which is integrating from 1 to 1, f of t dt. This is thankfully our easiest one. Now we wind up losing all this area, so we get 0, because we're not even talking about a region. We're going from 1 to 1. H of 1, we just did. Now I think you want h of 4, which is to integrate from 1 to 4. And now things kind of feel normal again. Bottom number is smaller than top number. This is kind of normal. We're going to accumulate the area from 1 to 4. So effectively, we're just talking about that rectangle. That should just be half of 3 times negative 3. Now that this is kind of normal, the base is actually positive, and we're down, so the height is negative. So this should be negative 4.5. I know it doesn't ask you on your paper to do h of 5, but I think it's actually probably worth it for the graphing part. But h of 5 is the integral from 1 to 5, f of t dt. So we should still have that rectangle, or sorry, that triangle, which is 3 and negative 3, and then this just skinnier triangle, which is 1 by 4. So this should just be that negative 4.5 we got before, plus an extra half of 4 times 1. Left to right, positive base, up, positive height, that's an extra 2. That's negative 2.5. And then h of 8 is just asking you to go from 1 to 8. So you're finally going to keep that triangle we just accumulated and accumulate this big giant rectangle that's just sitting right there. So that should just be our same standard negative 2.5 plus that big giant rectangle, which is 3 by 4. So negative 2.5 plus 12 should get us 9.5. So h of 8 is 9.5. So we're sitting pretty. So now we're going to basically look at those same exact questions for h about increasing, decreasing, maxes and mins, and I'll even sprinkle in a little concave up, concave down, and we should be able to make a giant conjecture here about the relationship between the function and then the function you're sort of integrating and how they're related. So if we want, we might as well just start with the graph. I probably need some more space because I want to go out to 8. So that's negative 6, negative 4, negative 2, 2, 4. We included 5, so I'm going to highlight that. That should be 10, 8, 6, 4, 2, negative 2, negative 4, and I think we should be okay. So let's plot some dots. We've got h of negative 6 is negative 3 1/2. It should be here. H of negative 4 is 1/2. H of negative 2 is 4 1/2. H of 1 is 0. H of 4 is negative 4 1/2. H of 5 is negative 2 1/2. And H of 8 is 9 1/2. So all the way up here. So there are our graphs, just with a bunch of dots. Now I do ask you that increasing, decreasing stuff, and you can kind of just see that this function is increasing from negative 6 until that peak at negative 2. Then it's decreasing from negative 2 until we get to 4. Which means if we go from increasing to decreasing, we should hit a max at x equals negative 2, and we should hit a min at, now we start increasing again at 4 until 8. And our min happens at x equals 4. Those are all the same. Exactly the same thing. Totally the same as the first function when we did it for that function g, when we had negative 6 as our sort of anchor point. So we're getting all the same things. This one's going to feel a little weirder in my explanation about concavity, and that's, I think, really where that one sort of messes stuff up. Because you start talking about backwards, upside-down rectangles, which sounds insane when you say it out loud, but actually kind of makes sense in the context of this problem. So since our rectangles are backwards, things are a little weirder. So if we start with negative 6, since we're anchored to 1, that first value is represented by all this area. So we have this dot. And then what happens as you make the x bigger? You start to lose these backwards rectangles. And since all these rectangles here have negative bases and up positive heights, you start to lose negativity. And since you're losing negativity, you wind up increasing. Now what's weird is also these rectangles, as we sort of go, are getting taller and taller and taller and taller. So their heights are getting bigger. So each one we wind up losing is like more negative than the one that came before it. So we're losing negative numbers, like we're losing negative 1, then we lose negative 2, then we lose negative 3. So we're increasing because we're losing more negativity as we move from left to right, which means we should be curled like this. Losing more negativity should mean we increase faster and faster and faster. Then we start to lose negativity, but slower and slower and slower and slower and slower, because each one just gets shorter and shorter and shorter and shorter. So that means we increase still because we're losing negativity, just losing it slower and slower and slower. Now, these ones get sort of weird because these are upside down, which means they have a negative height, and they have a negative base, and as we lose these, we're losing positivity. So we're decreasing because we're losing positivity, but those things we're losing are getting taller and taller and taller and taller, which means they have more and more area, which means they're bigger and bigger and bigger. So we're decreasing, but faster and faster and faster and faster as we lose that positivity. Then we start accumulating rectangles from nothing, and those rectangles are getting shorter and shorter and shorter and shorter, but we're going left to right, normal, positive base, and they're upside down, so that means the overall answer should be negative. So we start accumulating rectangles that are down, but they're getting shorter and shorter and shorter, so we start to get negative just slowly. That means concave down. Then we start to accumulate rectangles that are getting taller and taller and taller and taller, left to right, positive base, up, positive height, we should be concave up for a while, until we start accumulating the exact same rectangle over and over and over again. Between 5 and 8, the height of every rectangle is 4. So you just non-stop acquire the same value over and over and over again, which should mean you increase at a constant rate. So we're concave up from -6 to -4. We're concave down from -4 to 1. We're concave up again from 1 to 5. And then we're constant from 5 to 8. Those are exactly the same as from the first video. So, the whopping difference between video number 1 and video number 2 / function number 1, where you were anchored to -6, and function number 2, where you were anchored to +1, is ultimately, you should have drawn the exact same graph. Our graphs are the same. It'd be nice if I had them both and we had a Promethean board and we could just click back and forth real fast. But our graphs are exactly the same, except one's just higher than the other. So the big takeaway is, hopefully, when is this function increasing? When that function's positive. Right? When this is positive, this guy's increasing. When this guy's negative, this guy's decreasing. So you're looking for a function and another function where one of them increases when one of them is positive, one of them decreases when one of them is negative. The functions are exactly the same regardless of what number you apparently put here on the bottom. The only difference in the graphs is whether one's up higher or lower, or like a plus C. And then even the concavity, when this guy is increasing, this guy was concave up. So aka when f is increasing, the accumulator function is concave up, and when f is decreasing, the accumulator function is concave down, and when f is constant, the accumulator function has no concavity, aka it's linear. So we should be able to make a whopping connection between the relationship between h and f, and that thing is called the Fundamental Theorem of Calculus, and that's the thing we're going to learn on page 3.